So here I've got I don't know if you remember seeing some of these Phets. They're physics demonstrate physics simulations. They're pretty fantastic. Phet.colorado.edu. So if you go to the Phet site and you look up the hydrogen atom, there's this fun little models of the hydrogen atom and simulator and the different models of the hydrogen atom. And I never really talked about the billiard ball model, but it's that concept that the atom is the smallest possible thing and it can't be broken up into anything and it's just a hard mass. That's the sort of prior to the plum pudding model, prior to the discovery of the electron. So we can start with so if you look at this, I set this on prediction of the models, and you can mess with this if you want to come in here and see experimentally what really happens when you do these things. But I'm just going to look at the models. The plum pudding model, remember, predicts that the electrons are in just this mass of positive charge. And I guess I drew it like a pie, but a plum pudding, I guess I don't know what shape a plum pudding is. But anyway, this is fun. So there's your hydrogen atom, so it's a single electron, and the positive is just mushed around in the atom. And then the classical solar system. Ooh, look at that. Classical solar system has a electron going around a nucleus, but the problem is that it doesn't last very long, so it's kind of hard to watch. Kaboom, I love that. Um, and then the Bohr atom, which is the classical quantized orbits, the classical quantized orbits. We won't get to the de Broglie or the Schrodinger atom until next chapter, but let's just see where we are with our current model of the atom. One of the kind of cool things you can do here is you can actually, so here's just a light, a cool little light gun. These things do not really exist in real life, but you can turn it on and shine light on the atom and see what happens when you shine. Oh, look, I made the electron jump up to a higher energy level. So I have the energy. So let me turn that off for a second. Let me turn that off for a second. So you can change the color of the light that you shine on the atom. Well, if I can turn that on, you can see yellow light, red light. It's kind of fun. This is almost like a video game. You can shine different light on the atom, and what it's showing are actually photons, because that is the correct model of light when it interacts with an atom. You really need to think of the photon model of the light when it interacts with an atom. It's a really good point. Okay, let me turn the light off. And over here, it tells you about, I've actually been messing with this, so hey, let me reset. It tells you about how many photons have been emitted by this atom. So when I shine light on it, right, that's one thing. But what happens, why do I shine light on it? I shine light on it to try to excite the electron in the atom up to higher energy levels. And then when it's excited to higher energy levels, it can go back down to lower energy levels, and we will detect that transition by detecting photons being emitted from the atom, as opposed to the photons that we're shining on the atom, because the photons we're shining on the atom are actually directional, right? We're shining light in this direction. When it emits photons, it's going to emit photons in all directions, so we'll be able to detect the difference between the light we're shining on the atom and the light that we're getting out of the atom. Okay, so what can we do? Let me pause this for a second. So I've got, starting with the billiard ball model, sending in some blue photons, and you can see they bounce off when they hit that. Let's go to classical solar system model. Now notice what they do is that they sometimes have collisions with this electron. I don't know, it's not that interesting. And the electron bounces around in the atom. Oh, look. Oh, okay. I didn't realize that you could make this so the electron is emitting light when it gets excited by those blue photons. The classical solar system model, not much we can do here because it doesn't last very long. How do I reset that? Let's see what the energy level diagram looks like. Let's see what the energy level diagram looks like here. Oh, there is no energy level diagram for that one. Okay. Kaboom. Huh, how do I restart? I don't think it's this. Okay, so it looks like to restart the classical solar system model, you just click on it again, and boom, boom, boom. Nothing much we could do except just to look at the energy level diagram, right? It sort of falls in energy really quickly, but it's a continuous thing, and that's what's important here is that the energy it would emit is continuous as opposed to being discrete. It just goes too fast to really tell. Can we slow this down? What happens if we do that? Does that slow that? Oh, it does. It slows it down. Look at that. Oh, that's kind of neat. I didn't realize that. Okay, so we can go ahead and slow that down. You can see that fall slower, faster, faster. I mean, faster, faster. Okay, let's go to the Bohr atom, which is where we are now. Here we are at the Bohr atom, and now we've got the quantized energy levels. The electron is in the ground state. In order to get it above the ground state, we have to hit it with a photon, but we have to hit it with the right photon, right? And that's where we need to give it enough energy to go up 1 or 2 or 3 or 4 or 5 energy levels, and you can see these are the energy levels here. Now, to get a little help here, we can look at the wavelength needed to move up in a level. So, for example, to go from the ground state to the first excited state, from n equals 1 to n equals 2, we need 122 nanometer light. So let's go ahead and do 122 nanometer light and wait for, oh, a collision. Nope, that was not a good collision. Oh, duh, that was blue light. We got to get the 122. There we go. And it jumps up. And you can even see it over here, n equals 2. Remember I said it doesn't last very long. It's just that we've slowed this down, so it stays up there for a little bit. Boom, it goes up there, and it doesn't last very long. And when it goes down, look what happens. It actually emits a photon, right? And there's the emitted photon when it goes down. Okay, so let's say we want to go from 1 to 3. We can do 103 nanometer light, 103 nanometer light. Boom. So now, oh, it only went up to 2 because I guess, let's wait for it to go back down. 103, did I? Yeah, I did reset that. Okay, there you go. Now it goes to the third energy level. Now notice what happens is it can fall all the way back down to n equals 1 and let out a certain type of photon, or, let's wait for it to, wait for it. I guess I could speed it up again. There, it goes up to n equals 3. Oh, fell back down to n equals 1. It doesn't go to n equals 2. Let me speed it up a little bit. Speed it up a little bit. Okay. N equals 2. There. So see, it went down to n equals 2, then n equals 1. And look, it's letting out a red photon because that's the transition from n equals 3 to n equals 2. N equals 3 to n equals 2, look, over here, that's 656 nanometers. That's a red photon. So sometimes it goes from 3 to 1, and it'll emit a UV photon. Sometimes it'll go from 3 to 2, and it'll emit a red photon. And presumably the calculations they put in here are the correct probabilities because there's a certain probability it'll do this go from 3 to 2 or 3 to 1. Although it looks like it might just be alternating, but maybe it is a 50-50 probability. And we can try to make it go up to higher energy levels. There's only a certain, our photon gun is not perfect. It's only got a certain range, so we can't get down to these lower wavelengths. I think, what's the lowest wavelength we can do? Oh, we can get down to the lower wavelengths. So, oh, look, I got all the way up to n equals 6. Oh, neat. And so then, you know, sometimes it went to 4 and then 2 and then 1. N equals 6, 3, 2, and then 1, and different color photons are being emitted. You can play with this, and it's kind of fun to play with. And then what's kind of neat is the de Broglie wavelength. The de Broglie atom. Let me turn off the photon gun. We haven't talked about this yet, but it basically ascribes wave-like properties to the electron, which is correct. We'll learn that in the next chapter. And so instead of the electron being a particle that's going around, it's actually got a wave-like nature as it goes around the atom. And so hence that's how what they're trying to depict here. You can still shoot photons at it, and you can still excite it to higher energy states. Let's find a higher energy state that we can excite it to. 122, 122. You can either move this or with your cursor, or you can put in a number. Put in 122, and look what happens. It goes to a higher energy state. It turns into a different wave, right? That's kind of a wave that's going around. You just can't tell because it's such a small circle. That we'll get there in the next chapter. The Schrodinger atom is a whole nother thing. And it also allows for what's called the fine or hyperfine splitting of the atom. So that's one thing. One of the problems with the Bohr atom is the Bohr atom does not predict these additional energy levels that we see in a real atom, which we haven't talked about yet, which is the fine and hyperfine splitting of the energy levels. The energy levels actually can be split into additional energy levels, and we get a fair and more the emission spectrum. Basically, when you look at the atomic spectra, when we saw the glowing gas tubes, when we look at the atomic spectrum, we see a red line. If you look really closely, that red line is actually split into a number of other lines. That's the fine splitting or the hyperfine splitting, and that's what we're showing in the Schrodinger atom here. That's a future topic. Okay, there's your demonstration. You can come in here and play with this and see and sort of start to understand the models of the atom a little better. But we are going to move on now to finish up the chapter and start to talk about the wave nature of matter.